So I'm more of a social science person. Chi-squares can also be used in a really biological sense. And this particular example we're going to use is with quadrats. So if you can imagine, some of you when you plant your garden might plant sister plants or plants that help each other. So like a lot of times you'll plant corn and beans and squash because they're nitrogen fixers, they change air quality. We know that they exist really well together. So you may go into an ecological area and you might say, starting with that quest model, I noticed that these two plants are together a lot. Is there mutualism happening? Are they codependent? Do they coexist? And it would be really difficult to make all these quadrats or do transects and decide which plants count and which plants don't count and how big the plants are. And that could become a really very messy study when we really just want to know, do these plants coexist together? Is there a relationship, right? And so in this version of the chi-squared, we're not testing a sample versus the population. We're testing for independence. And it looks just a little bit different. I'm going to pull up the slide here again. So we have to have categories for this, just like we did for the last one. We still have to have a way to calculate the expected values, but it's not necessarily going to be based on a population. It's going to be based on something called a contingency table, which sounds very scary, and it's just not. It's not scary at all. A contingency table is really just, it's also known as a two-way table sometimes. It's really just helping you kind of organize your data so that you can continue to perform the chi-square test on variables that could be independent. So for this, and it's similar, our null hypothesis is that these two things are independent. Plant A, species A, is independent from species B. They can be wherever, they're not related. Our alternative hypothesis would be plant A is related to plant B. So they have some sort of interdependence. They are not completely independent of each other. So they kind of need each other to survive. Now, the good news is this is really cool, especially with social science data. You can really get, this would be sort of that, does gender influence political leaning, right? We can get into some of these really difficult questions, and we can also simplify some of the biological questions. The challenging part is that it requires a lot more calculation on our part. So if you kind of haven't been following along, now might be a good part to kind of click around because we are going to kind of go through this. So this scenario is based on this quadrat over here, and you can see species A and species B are listed. So species A is sort of this green spiky species, and species B is this yellow flower. And rather than going through and counting each individual one and figuring out where they occur, we have them in these 5 quadrats. And all we want to know is, are they present or are they absent? And in how many quadrats? So here's my first contingency table. So for this first box right here where it says 3, that means of my 5 quadrats, in 3 of them, there was both a species A and a species B. And you can count them here. 1, 2, and then there's one behind the panel that I can't see. In one of my quadrats, species B was present, so the yellow flowers were present, but the green spiky was not. In one, species A was present, but species B was not present, or was absent. And then in none of any of my 5 quadrats, we never had where both of them were absent. Now this is hard data to like predict, right? It is hard to be like, oh, that's a lot of numbers. I don't really know what's going on. And that's why these contingency tables are really important. So for calculating the expected values here, the really nice part is you don't have to do as much thinking. There's a formula for this. So because we have these categories of absent and present and species A and species B, we're going to use a really simple formula to calculate this. So we're going to say, okay, if everything was fair and everything was equal, then this expected value would be the row total. So I'm looking at this cell right here, right? It would be the row total, which is 4, times the column total, which for this value is also 4, oops, divided by the total number of our samples, which was 5. So one more time, that gives me 3.2. Okay, so one more time, I'm looking at just this one right here. We're making a new table. And in order to find the expected value, I'm looking at this row total times the column total divided by the total number of quadrats. So we're going to do that again for each one. Not hard math, just making sure your tables are organized. It's like French cooking. You got to get everything set up first before you can do all the hard stuff, right? So for this one, now we're looking at where species A is present and B is absent. So now I'm in this column. I'm going to say, okay, my row total was 4. My column total now is 1. And we're still going to divide that by the total of 5. I'm going to do that for the next one. So now I'm back down here. A is absent, B is present. So now my row total is 1. My column total is 4. Oops. Got to make sure you hit the right function. And we are going to divide that by the total again, is 5. And then one last time. Okay, it doesn't matter that this is 0 because remember, I'm not looking at the value. I'm looking at the row total and the column total and dividing by the total. So my row total is 1. My column total is 1. And I'm going to divide that by 5. So now I have my expected values, and now I have something that I can compare in my chi-square test. So that means that if I look at these, I do that common sense check, they look pretty close. So they look like, okay, these match. My observed and my expected are pretty close. They match pretty tightly. That should be good. But we still need to run the chi-square statistic. It's hard to say. Now this is where it's kind of sad. Google Sheets is just not smart enough. Excel is not smart enough, but you are smart enough to figure out how to do this. And that's great. That's perfectly okay. Because what we're going to have to do is we are going to have to calculate the chi statistic for each of these 4 boxes. You're probably like, wait, what? That sounds so difficult. Look at that formula. It's so hard. It's not. It's really not hard at all. We just like to trick you and think that it's hard. So for this formula, it says we're going to take the sum, which we'll do at the end. We're going to do the observed value. So that's from our first contingency table, minus the expected value in the same spot from our second contingency table. We're going to square that, and then we're going to divide by the expected value. So again, a lot of really simple math that, thank goodness, Google Sheets helps us do. So we're going to go equals. We need the parentheses because order of operations is happening. So we're going to do the observed value, which was 3, minus the expected value, which was 3.2. I'm going to use the caret, which is shift 6, to square it. And then I'm going to divide that by the expected value again, which is that same box. That is my chi-square statistic, which doesn't mean anything to you yet, and that's fine. So we're going to do that for each of the boxes, and you kind of have to go in and do it by hand. There's no good way for Google Sheets to follow what you're doing. So you're going to go equals, parenthesis, the observed minus the expected, end parenthesis, caret, square, divided by expected. Okay, and then we're going to do the same thing. So equals, parenthesis. We're going to do the observed minus the expected squared divided by the expected. And then one more time, we are going to do equals, parenthesis. It kind of thinks it knows what we're going to do, and it's not always great at predicting. So I definitely recommend going all the way through. Minus expected squared divided by the expected. Okay, So I have this already set up. I have already summed everything I need. So the table has summed this way. So you can see I have the sum of these two cells, and I have the sum of these two cells, and that gives me a test statistic of 0.312. Wait, we're not done. That's not a p-value. Not a p-value. It's a chi-square value. So now we have two options. We can run it in here, which is pretty easy. If you feel more comfortable running it in a calculator, I actually gave you a calculator here. But to do that, to do either one, we need to know the degrees of freedom. And like I said, the degrees of freedom is just the number of categories minus 1. Now, because we're in this like kind of duplex or 2x2 table, we don't have 4 categories. We really still only have 2. We have species A and species B. So our degrees of freedom is still just going to be 1. Our test statistic we have, that's our total. So we took the sum of all of these chi-square values, and that's what's right here. That's what our formula says we need to do, add up all the chi-square values. That gives us our test statistic. 3, 1, 2, 5. And then now, here's the difference. Where we ran the chi test before, we now want to run the chi distribution. So here I'm going to run chi, chi-squared distribution. And that is going to be, you can see it walks you through it, our test statistic, our degrees of freedom, and then pretty much always a normal distribution. Our assumptions are pretty valid on a chi-square test. There aren't a lot of assumptions besides your logic. So we can go ahead and do that. So test statistic, our degrees of freedom, test statistic, comma, degrees of freedom. And then, doesn't like me today. I'm on a different keyboard than I'm normally on. My apologies. Distribution, test statistic, degrees of freedom. And then remember, in Sheets, not in Excel, but in Sheets, you actually have to type the word true. And then that gives us a p-value of 0.42. That is well above 0.05. So we can say that it's not significant. These species do not cohabitate in a significant way. So that's just kind of 2 different ways. The first one is running a sample against a population, and the second one is testing, are these 2 different categories related to one another? And there are, like I said before, there are links in the bottom of mine. If you have more questions about contingency tables, that's just one really small sample size example too. Any change in that data would have a big impact on the p-value because the sample size is so small. In the interest of time, if you're interested, there is a little bit more on that worksheet, but I'm going to go ahead and let you explore that on your own.